What's going on, you guys? So today we're going to do decode ways. So I haven't seen this problem yet, and we're going to try and treat it like an interview. So I'm going to be narrating my thoughts, and I'm going to be doing everything as I would with an interview, just talking to my computer. So I have this on my computer. I'm going to set a 45-minute timer, because that's usually the amount of time. Well, I mean, you can have anywhere from 25 to 45 minutes. I'm going to give myself, let's do 30 minutes. 30 minutes is, if I can solve this in 30 minutes, that's a good sign. Okay, so I have this problem on my computer, so I'm going to do it there. But if you wanted to follow along, you can find it on the browser here. Just search Decode Ways LeetCode and you'll find it. Okay, let's start a timer. Okay, and we're on, so let's go. Okay, decode ways. A message containing letters from A to Z can be encoded into numbers using the following mapping. Okay, so it's like the ordinal mapping. So in Python, if you go ord I think it's going to be different. Well, lowercase a is the right number. Well, oops. Okay. Anyways, like lettering of the alphabet. So A would be 1, Z 26. That makes sense. Okay. So let's see. Decode, encoded message. All the digits must be grouped, then mapped back into letters. What is going on here? Okay. Okay. To decode an encoded message, all the digits must be grouped, then mapped back into letters using the reverse of the mapping above. There may be multiple ways. What? Okay. To decode and encode, all the digits must be grouped, then mapped back into letters. Okay, so we have some digits, and we're going to be mapping them to letters. Okay, so for example, so we've got an example here. Cool. So 1, 1, 10, 6, 11. Oh, okay, because this can be, so this string of numbers can be pulled apart into different digits. So it could be, we could get different mappings. I think I see what's going on here. Okay. Okay. And we know that each digit has to be less than 26. I think. Okay, because it looks like we have uppercase letters only in our message. Okay, so we know that these digits have to be in 1 to 26. Okay. Cool. All right. Okay, note that the grouping 1, 11, 06 is invalid because 06 cannot be mapped into F, since 6 is different from 06. Okay, interesting. Good to know. Okay. Given a string S containing only digits, return the number of ways to decode it. Okay. Alright, so in this case, there's 2 ways to decode this 11106. Okay. Given a string S containing only digits, return the number of ways to decode it. The answer is guaranteed to fit in a 32-bit integer. Okay. Example, okay, we got 1, 2, there's 2 ways. Could be decoded as AB, or as 1, 2, or the number 12. 1 and 2 or 12. Okay, got it. 226, we can break that up as 226, 22, 6, or 226. Okay. Okay. 0, output 0. There is no character that is mapped to a number starting with 0. Okay. Let's see. Okay. So the only valid mapping with 0 are J10 and T20, neither of which start with 0. Hence, there are no valid ways to decode this since all digits need to be mapped. Okay, that makes sense. Okay, another example. We got plenty of examples. That's nice. All right, so O6 cannot be mapped to F because of the leading 0. 6 is different from O6. Got it. Okay. So if a number starts with 0, we can just return. Okay. The string is going to be 1 to 100. S contains only digits and may contain leading zeros. So we can right away just say, you know, if S0 equals 0, let's return 0. Deal with some of those edge cases. Okay, so let's think about this. Let's walk through a few examples and see what's happening here. Okay, so 1, 1, find 1. Okay. All right, so what's happening here? So how can we break this apart? We can do, this could be 1 or 11. Okay. And, okay, so if we're just looking at the first 3 numbers, there's 2 ways. Let's see, 1 and 11, or 11 and 1. Okay, so there's 2 ways to break up the first 3. Wait, no, we cannot do, can we do 1? So we can't do 11 and, not 1, but 11 and 10. So we can do 1, 11. We can do 11, and this has to be 10. Okay, and then this has to be 1, and this has to be 10, because we can't have a leading 0. Okay. So how do we do that? Let's think. So that we're adding spaces to our string. So the question is like, where do we add spaces? We can add anywhere from 0 up to, 1 in between each number. So spaces to add. It's going to be less than, let's see. So in this case, 1 here. What's the max? Let's see the max. So we can do 1 between each. So 1, 2, 3, 4 spaces here. So 1, 2, 3, 4, 5. Okay, so it's len of s minus 1. Yeah, so len of s, number of spaces. And what's the minimum amount of spaces? If we get one number, if it's just one number, we could add 0 spaces. So it has to be greater than or equal to 0. Okay, so spaces to add, we can go from 0 to length of s. Okay. And so so a brute force solution would be to create all the possible strings, and if it's a valid string, add it to our total, and then return the total at the end. So this is going to be pretty intensive. But how would we, so the question is, okay, so a brute force, create all possible strings by placing, for spaces in spaces to add, in spaces to add, so range, so we know that spaces to add goes from 0 to the length of s, so we'll say a range of length of s. So for each one of these spaces, we're going to create all permutations and for permutation in permutations, if valid, then we'll increment our total, and then at the end we're going to return a total. Return total. And we would say total equals 0. So, okay. So, like for example, if we were only gonna do one space, then the possible ways would be, let's see, so, so there, let's see here, there, there, and there. Oh, so 1, 2, 3, 4. Okay, and then for all of these, we would check and see if they're valid. So none of them are valid because all these values are outside of the 1 to 26 range. But anyways, you can see that this is gonna, like amongst all the invalid ones, we'll have the valid ones, and we'll be able to count those. We'll be able to do our valid check. You know, check that there's no leading 0, check that it's between 1 and 26, and we would, if those cases hold, then we're gonna increment our total. So our valid is each number, so numbers in between, so 1, so it's greater than 0, so each number is in 0 to 27. So this goes from 1 to 26, and what else? And no leading zeros. So if those cases hold, then we'll increment by 1. So if each number is in that range and there's no leading zeros, then we'll increment by 1. Okay, so let's think about, okay. So in this case, there are, how many? 1, 2, so it's n minus 1, choose 1. N minus 1, choose 1. And then n minus 1, choose 2. N minus 1, choose 3. N minus 1, choose n minus 1. And you have to add those all together. And this is like the number of operations. So is that n to the n? So this is on the order of n raised to the n. Wait, no, you add these. You add these together. Hold on. So n choose 1. We're not multiplying. Okay, so n choose 1 is n minus 1 factorial over n minus 2 factorial times 1. So it's just n minus 1. Wait, is it O of n? Does that work? Okay. Let's think about how does 1 answer? Is there any way we can? How can we add dynamic programming? Like how does the solution of 1? Is there any subproblem that we could solve that builds on each other? Let's see. So let's start with 1. And let's check time. See where we're doing on time. Not sure on time. Okay, 14 minutes. So we got 15 minutes to go. All right, 1. Okay. Is this valid? The question is, how does 1 relate to like 1, 1? How does 1 relate to 1, 1, 0? So I'm trying to see like how, is it possible to do like a bottom-up dynamic programming approach where if we solve like one little subproblem, we can build on it for subsequent steps. So if we see that 1 is valid, yeah, so it's kind of stumping me. Okay. So hopefully you would get some kind of a hint at this point when you're stumped and you're not sure how to apply the technique to the problem. Let's see. Yeah, I'm really stumped on this one, guys. So that'll happen in the, so that when that happens, when you get stumped, like hopefully you build up like a game plan of like trying different things like you can ask yourself like, all right, well, can I use a hash map? Is there, like, if you get the brute force part, can you think of like any repeated work that's happening that you could remove either with a hash map or by doing dynamic programming? So maybe, all right, here's something we could do. We could run some like small examples through our brute force approach to get a better feel for what kind of work is happening, and then see if there's any repeated work that we could optimize. So that seems like the best approach right now. So let's see. Okay, so let's start with s equals 1. Let's just see what happens here. So for spaces in range, okay, so in this case we're only going to do 0. Wait, so okay, so this is for spaces in range len 1. So this is going to go through this one time, create all permutations. You know, what are all possible permutations here? You know, 1 space 1. Maybe this is a base case, and so we say if len s equals 1, then return 1. Because there's only one way we can have this here. Okay. Now what about, let's do s equals 1, 1. Okay. Let's see. So what are the possible permutations here? Let's see. So for spaces in range len of s, okay, in this case s is 2, so it's going to go 0, 1. We're going to go 2 0 spaces in 1 space. Okay. I guess, you know, it's possible that, yeah, it's possible when there's 0 spaces, it's possible that there is, wait, it looks like, so this is, I don't think we need that if statement, because for 0 spaces, when we create permutations with 0 spaces, we're just going to return the string itself. So this should work. We don't need any extra like if statement to handle size 1. Okay, for size 2. So we're going to do 2 loops for 0 spaces and 1 space. Okay, 0 space. So what are the possibilities? 11 is a possibility. Now 1 space, we can do 1, 1. And that's it. Okay, so we got 2 possibilities for 2 possibilities for 11. Okay. Interesting. Okay. So total equals 1. Just trying to keep track and see if there's any patterns that we see. Okay, so let's do S equals 111. We'll create all the permutations. So for 0 spaces, we got 111. For 1 space, we've got 1-11. We've got 11-1. And so this goes, spaces goes from 0, 1 to 2. So now for 2 spaces, we can do just this. Okay, so there's 4 possibilities for this guy. Total equals 4. Okay, interesting. And how can we use previous runs through to build on? Is there any? Is there anything? Is there any way we can use previous runs? Is the question. Okay. Checking time. We've got 21 minutes, so we've got 9 minutes left to see if we can find any optimizations here. Do better than brute force. Okay. Okay, let's do S equals, let's do 4. Let's just keep going. You know, maybe we might see something. So 0 spaces, we just get 1, 1, 1, 1. 1 space, 1. There's only one way to do 1 space. 2 spaces, 1, 1, 11. 1, 11, 1. 11, 1, 1. Okay, and 3 spaces. Okay, 1, 1, 1. 1. Okay, so interesting. Okay, total, you know, it's frustrating, but you gotta learn how to handle these situations. Let's see, how many is that? 1, 2, 3, 4, 5, 6. Okay. Interesting. 1, 1, 2, 6. Okay, interesting. How is length 4 related to length 3? Are they related? Is that the question? That is the question. Oh, look, so for 3, if we look at 3, and we ask ourselves, like, how can we place an additional 1 here? Wait, oh, this is invalid, hold on. 1, 1, 1, 1, that's not valid. And 1, 1, 1, that's not valid, okay. Okay. Okay, so if we look at the examples for 3, And we ask ourselves, like, how would we place an additional 1 in these? And how many ways can we do that? Let's see. So how can we get from 3 to 4? So we could, let's see. One, two, three. Okay, the question is, how do we get from, this is 3 and this is 4. How do we get from 3 to 4? Okay, so we can say, we can add 1 here. We can add 1 at the end. Okay. And where else? And then where do we add 1 here? Here. And where do we add 1 here? Here. Wait. Let's see here. I think this is the right idea, you know, like, okay, so how do we get from 3 to 4? We can add 1 in 2 places. So we can add 1 here. We can add 1 here. Okay, where can we add 1 here? Add 1 to the end. Add 1 to the end. Add 1 to the end. But also add 1 to the beginning. We might get there, we might. Oh, okay, so there's a couple of ways we can do this. Alright, so, alright, so we can add 1 there. Yeah, hold on here. Let's just do the first one. How can we add 1 to this? Okay, we can add 1 here. We can add 1 here. We can add 1 here. Okay, so it looks like that's all. And then where can we add 1 here? Here. And here. And also this one. But we've already got that one. Where can we add 1 here? We can add beginning. Or at the end. That creates the same thing. 1, 2, 3, 4, 5, 6. 1, 2, 3. 1, 2, 3, 4, 5. Oh, this is 5. No. 1, 2, 3, 4, 5. 1, 2, 3. Oh yeah, I copied 1 here. Okay, so we can kind of get to 4 from 3. This one's tough. So it looks like we're going to run out of time here. We came up with a brute force solution, but we had trouble, I had trouble coming up with a bottom up DP. So now let's take a look at the solution. Okay. Save that. And let's go with, let's take a look at the Python first. Okay. Easy to understand explanation. It's my first post. Please let me know it's helpful. Okay. Variation of nth staircase. Interesting. That's why I think that, some people say don't do the easy problems, but the mediums and hards, they're just building, they're like a few easies, like just melded together. So if you can break down a tougher problem into an easier sub problem, then it's valuable to do those easies. That's because the nth staircase one, that's an easy dynamic programming. Okay, so let's see. We generate a bottom-up DP table. The tricky part is handling the corner cases, like when there's a 0. Okay. Most elegant way to deal with those error corner cases is to allocate an extra space, dp0. Let dpi equal the number of ways to parse the string s from 1 to I plus 1. Okay, interesting. I plus 1. Parse the string I 1 to I plus 1. Okay. For example, 231, index 0, extra base offset. So we're going to say dp0 equals 1. Okay. dp1, number of ways to parse 2. What? Okay. There's just one way. Got it. Index 2. Number of ways to parse 2, 3. Are 2 and 2, 3. Okay. Let's see. So dp2 equals 2. Index 3, number of ways to parse 2, 3, 1. 2, 3, 1. 23 and 1. So there's 2 ways. Okay. Wow, so we started off along the right path, right? We were just trying to start with size 1, size 2, size 3, figure out how many ways we could parse them. But let's see where we missed. Okay. Not s, return 0. dp, he sets it 0 for length of s plus 1. Okay. Initialize to 0. Base case, dp0 equals 1. dp1 equals 0. If s0 equals 0, else 1. Okay. Okay, so now 2 to len of s plus 1. We're going to fill in all the other dp values, one step jump. If int, so s of I minus 1 to I is greater than 0 and less than 9, so if it's a valid number, dpi, we add the previous amount. Interesting. Why do you add the previous amount? What? Oh. Interesting. So we know the number of ways to add 2. There's only 2 ways to break up 2. Barring the edge case, there's only 2 ways to parse a length 2 string. Oh, so if we get a length 3 string, we can just take the number of ways to parse length 2. Okay. But, okay. No, so 4 would equal what? It would equal 3? Why isn't it just 2, 2, 2, 2, 2? Why isn't it, why isn't dp, what I'm not sure of is okay, dp is, 0 is 1, 1 is 1, 2 is 2, 3 is 2. Why isn't it just 2, 2, 2, 2, Let's see. Let's see what they do. Oh, that's for a 1-step jump, and then a 2-step jump. Okay. So if we get a number between 10 and 26, what do we do? Wait, what? We take the value from 2 steps back? What? I don't get it. Okay. Handling starting with 0. Alternative, I would recommend treating as an error condition and immediately returning 0. It's easier to keep track and it's an optimization. 2. Pay close attention to your comparators. For 1, you want 0 less than, not 0 less than or equal. For 2, you want 10 greater than equal. Okay. All right, let's run. So it's not making sense yet, but I like to run through an example and see how the values of like dp and like s of this value, see how it's changing. Okay, so let's do that. Okay, so we've got our code here. We're going to say dp. We'll say s is, we can look at an example, edit, we can grab an example. We'll do 11106 because we know the answer to this one. Okay. Wait. There's only 2 valid bytes. Okay, so we'll do 11106 because we know that. Okay, so one 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 zero six, and we're looking for 2. Expected equals 2. Okay, fair enough. Let's set up our variables and see how they're changing over time. Okay, so we're going to bring s down here. dp is going to equal 0 for len of s plus 1. Okay, so len of s is 1, 2, 3, 4, 5, 6. So it's going to be 0 to 5 in here. So 6 values, 6 zeros, 1, 2, 3, 4, 5, 6. Okay. And so dp0 is set to 1. dp1 equals 0 if s is 0. If s of 0 equals 0, else 1. In this case, 1. So let's make sure to do an example where, I don't know, say it's 0, 1. Okay. So we'll do that one next. Okay. So so what are we going to do with I? Keep track of I like this. Okay, so I is starting at 2. Right there. Okay. We can label this with the indexes. So we'll do 0, 2, 3, 4, 5. And I think I is going to be, yeah, I is important for our string. So I is starting at 2. I starts here. Okay. So if s of, okay, 1 to, s from 1, wait, 1 to 2, 0, 1 to 2, 1 to 2. So just this value, 1 to 2 is just 1. If it's in 0 to 9, which it is, we're going to say dp of 2. Now let's also add the indexes here, so we don't have to do that. Okay. 2, 3, 4, 5. 0, 1, 2, 3, 4. Okay, so I starts at 2. If s from 1 to 2, which is just 1, it's in 0, 9, it is. We're going to set dp of 2. dp of 2 equals dp of the previous one. Okay. And then what? Okay. Now if s from 0 to 2, so 11, if 11 is in, then we say dp of 2. Let's keep our I here too, so we don't have to remember where that is. Okay, so dp of 2, we're also going to add dp of 0, so 2. Okay. Gotcha. Now we increment I. I is now 3. Okay. Then we say, all right, so if one, this in this case from S from 2 to 3, which is 1, is this in 0 to 9? Yes. So we'll say dp of 3, we add the previous value, so 2. Okay. Next if statement. So S from 1 until 3, which is 11. It is in the required range, so we add. We're gonna add the 2 steps back, so we're gonna add 1. Okay. This, I mean, the logic, it doesn't make sense to me, but you know, maybe if we do a few examples, something will pop up for us. Okay. So let's see, what else? Okay. Right, so we're incrementing I now. And I is going to go until 5 for every value. It's going to touch every value in DP. That makes sense. Okay. So int in this case, which value for the first for loop, or the first if statement, we're looking at the number S of 3. S of 3, which is 0. Is it in the required range? No, it's not. So we're going to skip that first if statement, the second if statement. We're going to look at S2 to S4, which is just 1 and 0, so 10. Is this in the required range? Yes. So we're going to add the value 2 steps back from DP. We're going to add 2. Oh, wow. So we're adding 1 or 2 every single time. What? Wait. Okay, still not getting it, but maybe that will come. Okay, so I is now up here. It's outside of S. So if S from 4 until this, which is 6, is this in the required range? Yes. So we're going to add DP4 to DP5. Okay, and now second if statement. I, in this case, 5 minus 2, 3, 0 to here. So 0, 6 is an invalid number. So we'll skip that one. Okay. And now we're gonna return the last value in DP, which is 2. Okay. All right. Well, doesn't really make sense to me, but that's okay. We'll keep going. I wanted to give you guys a real example of like how do you, when you don't know what's going on, how do you figure it out? And you just have to walk through a bunch of examples. So let's take a look at the C++ solution. The awesome thing about LeetCode is like there's many different solutions to the same problem. So we can, maybe if we don't understand one, we can understand a different one. Okay, so what's going on here? F of n. What? I just have no idea what's going on here. Maybe we're going to skip this one. Yeah, we're going to skip that one. Let's check out the Java one. Okay, so this one looks better. It's got a lot of upvotes. Okay, so I used a DP array of size n+1 to save subproblem solutions. DP of 0 means an empty string will have one way to decode. DP1 means the way to decode a string of size 1. I then check 1 digit and 2, what is that? Okay. I then check 1 digit and 2 digit combinations and save the results along the way. 1 and 2 digit combinations. Okay. In the end, dpn will be the end result. Okay. So it looks like a similar approach as the last guy, where he had 2 if statements and he was checking for size 1 strings and size 2 strings. So it sounds like this guy's going to do something similar, just in Java. And maybe we'll walk through another example and see if that. Sometimes you can build intuition just by walking through examples. It's a little tedious. It takes time, but it can really, sometimes a light bulb just pops. It's also good to like let this sit in the background of your head and move on and do something else. And we go for a walk, maybe try a new problem, and come back to it later. Sometimes that's a good approach too. Okay, so it looks like yeah, he's looking at size 1 and size 2. So this is the same approach. This is the same approach as the Python solution we saw. So I'm going to end this video here, but I'll add some resolution to the description. I'll tell you about like what I did later to figure it out. So right now it's not sinking in, but I expect that it eventually will. It might just take some time. It might take reading other examples and walking through examples and seeing how the algorithm is calculating that DP array. Yeah, all right, thanks for watching, guys, and stay tuned for the next one.